I want to spend some time to talk about Postgres architecture with extreme focus on the different processes that Postgres spins up to take care of all the auxiliary and maintenance and I/O in its software. It's pretty interesting once you kind of understand how Postgres works. We're gonna shed a light on all of this, all of the pieces and the components of Postgres. It's gonna be an interesting episode. Let's get into it. So what we're seeing here is an architecture diagram that I drew, and I wrote up a Medium article detailing this, all the pieces of Postgres and explaining them and how they are connected to each other, and what is the design goals of, and why Postgres picks certain architecture choices versus others. It's a very interesting article. I'm going to reference it below for you if you want to read it. But in this, I'm going to go over a summary and summarizing each pieces in this video / podcast. So maybe we can start with kind of an overview of what are we going to discuss, then we can pick pieces by pieces. So what we're looking at, for people listening in the podcast, we're looking at a diagram with all the pieces that I can think of in Postgres. There might be others that I have missed or maybe omitted because they are not relevant for this discussion. But the main process is called the postmaster process, and that's the listener. And if you took my courses, either the network or the backend course, you know that to listen for an interface on a port, you have to specify the address family. Like, is it IPv4, IPv6, and which one exactly? Am I listening on the Wi-Fi interface? Am I listening to the Ethernet? Am I listening to the loopback? Am I listening to the link local? Right? What am I listening at? And basically, sometimes most software just listen to everything. It's kind of a bad idea, and I'm really sad that that's actually the default, right? But it is what it is, just I guess for simplicity reasons. But yeah, so we have the listener, right? Postgres uses port 5432 as a default. And then clients connect to the database by specifying the target port as 543 and the address, right? Whether that's IPv4 or IPv6. Then there's backend processes. We're going to talk about what that means, right? You're going to see the word backend used a lot in Postgres. Pretty much everything is a backend in Postgres, right? Any process, they call it backend, right? And so it gets really confusing when you read the doc. Then there's shared memory, right? What is that? The buffer, the shared buffers. Then there's the background workers, and there is like a list of auxiliary processes, a list of standby processes that are used for maintenance and things like that. We're going to go through them. The auto vacuum workers, the wall senders. Yeah, that's basically a summary. We're going to go through each one of these. Let's go ahead. So we start with the first process, and this is kind of a lie, because this is technically not the first process that runs. There's another process that we're going to talk about at the end of the video that runs first, but let's, for sake of simplicity, we call this the postmaster process is the one that runs first, and it is basically the one that is the parent process for pretty much everything in Postgres. You see, Postgres is I suppose we have to define what Postgres really is, right? Postgres is a relational database system that is based on the idea of having multi-version concurrency control by doing an append model, where everything is an append. Everything that you do in Postgres creates a new tuple, as they call it. So you can have row 1, and then you update it. We don't update it in place, right? We create a new one with a version, right? We assign it a new tuple ID. But it is technically the same logical row. So you have one logical row, and that logical row can have 10 different instances of tuples, right? Physical tuples, and being the last one being the active one, effectively, right? Assume it's committed. And that's an interesting design choice that you don't see in other databases. That's what makes Postgres unique. There is advantages and disadvantages for that choice of the architectural design, but it's interesting. I talked about that in my differences between MySQL and Postgres video. Sometimes this design choice wins, sometimes it loses, right? And another key aspects in Postgres is that it is a process based, not threads, right? Everything is a processes in Postgres, and that's another interesting choice. The reason for going with process and threads, in my research and understanding, is basically stability, right? Threads back in the days were not stable, right? Processes were more stable, but definitely these days in 2023, threads technically is lighter weight and definitely stable, right? We don't have that problem anymore. So processes become kind of a bloat, if you think about it, because it's a harder, there is so much overhead with spinning up a process compared to spinning up threads, right? Yeah. There's the virtual memory address space. Every process will have its own, which means every process will have its own page table mapping. So that means also we're gonna thrash a lot in the CPU tiny area, which is called the TLB, which is the translation look aside buffer, which basically translates the virtual addresses to the physical addresses in the RAM, right? If you have a lot of processes, you're gonna have a lot of tables, and these entries are gonna be different, effectively, right? Compare this to threads, where we have those threads share the page table of the parent process, and as a result, chances you're gonna hit the cache hits and the TLB will be much higher than if those were processes, right? It's just, yeah. Is it a big deal? I didn't see any numbers to prove that it's a big deal, to be honest, but it is what it is. It's just understanding this is a critical thing. That's why when you open process, when you do top in Linux or task manager in Windows, you'll see a lot of Postgres processes. And we're going to talk about why that is the case, right? So yeah, the first process is basically the postmaster. That's the listener, and clients connect to this listener, effectively. And for each of these listener, when a client connects, and clients here are not really end users like you and I. The clients of the database is usually other applications, usually backend applications, right? It's rare that you have the user actually connecting to the database directly. We don't do that, right? We spin up a finite amount of web servers, and these web servers will have probably a connection pool, right? Whatever the maximum connection pool is, and then those connect to the database effectively, right? So there is a pool of connections. So the connection are limited by the number of applications, right? It's not like you're going in, it's not like you're spinning Nginx, right? Or a CDN or a web server like IIS that potentially can have millions of connections, right? It's not the case. Like end users don't connect to the database like that, right? But they do connect directly to a reverse proxy or a CDN, right? Or a web server, right? So this distinction is very critical because that's the economy of scale, effectively, right? What is important here is the understanding that every client that connects gets its own back-end process. That's the second component. For every connection, you get a brand new process. That will be a dead on arrival if this was like a web server, right? We never do that. There's always a pool of processes that actually limit the number of processes, right? Like Nginx spin up a process. Nginx is the same thing, like as Postgres. They use processes, they don't use threads, right? And they use a shared memory between these processes, like we're going to talk about in a minute. But those processes are limited by the number of cores by default. Like that's the auto mode. When you first spin up Nginx, and I think HA proxy behaves the same, it will spin up a process for each core or hardware thread, right? If you have hyper threading enabled. So that's what's gonna happen. But here, for every connection, you get a process. So I was really surprised when I saw that. That just doesn't scale if you have a lot of connections. And Postgres know that. That's why there's a property called max connections. And this is set to 100, which is a very low number if you think about it, right? It's like 100 connection, that's it, right? So because they know that's a bad idea. Like you don't spin up a process for each connection, right? If you have a lot of connections, soon enough your database will run out of RAM, right? And of course the CPU will just die, right? Because of context switching between all these processes. But yeah, so that's the design. We're gonna know that it's not as bad as I originally thought, because there is not much work happening here. It used to be before 9.6, but not anymore, right? Because of these guys, the background workers, right? Whatever work happens here is very minimal. Right, so there's the backend processes, and it's capped by the max connections because it's like 1-to-1, right? So that's the backend processes, right? So we have the postmaster. Every time the user connects, the postmaster forks a new connection, which it's very critical to understand here. Forking a process will technically copy the process, and because it's a process, it needs its own virtual memory space, right? Because that's how a process works. But if you do that, then you have to also copy whatever the postmaster had into the new virtual memory address. But Linux doesn't do that. Pretty much no operating system does that for optimization reasons. So they have the page tables point to the same location, but as you start changing, they do something called copy on write, or cow, right? So as users or the parent process start changing one part of the page, and those pages are like 4K in size, and you can change them. You can make them huge pages, and that's another discussion. Like this is something I'm researching these days, right? Huge pages in operating system. But these pages, like as you change them, they will be copied as we change, right? So just in case, right? So they are shared. Once you start changing, they're gonna be copied on write, right? So that they can stay distinct. So that's the trick operating systems play here. But yeah, everything is basically a fork here. All right. So all these processes actually need to talk to each other, right? Not per se, but like as they load stuff, as you read pages from disk, right? Whether these pages are table data, whether this is indexes, they're put in memory, right? And when you put in memory, this memory is actually called shared memory or shared buffers, right? Sometimes they call it, or buffer pool, many names, right? Yeah. This is where the wall records live. This is where the pages live, and pretty much everything that is shared is right here. And it's called the shared memory, right? This very, very critical piece of memory that every single process have access to. And this is allocated using this Linux command. It's called mmap, I think, right? And that's how you do it, like share a memory space between processes, right? And of course, you gotta be careful because you have to obtain mutexes and semaphores to avoid two processes writing to the same page at the same time. Right? You have to lock it and stuff like that. So things becomes later really pretty tricky when it comes to that. And that's true for both processes and thread, of course. Race conditions, you need to avoid it as much as possible, right? Then we come to background workers, which were introduced, I would say, in 9.6 with the parallel plans. A backend process, when it receives a query from the user, right? The backend process may execute a query in its local backend process, right? But optionally, if parallel plans were enabled, it can outsource this, right? The execution to one or more something called background workers, right? So this can, and this is a pool. Now this design I'm familiar with, and it's scalable, right? Because there's a limited set of processes and you can just throw things at it, right? This way we have predictability. We have this many number of processes and these do the work for us. If they are all busy, you get to wait. Clients get to wait, right? It's a predictable thing, as opposed to, like, let's say we don't have this background workers and every backend process actually does the work all the time. Then if 1,000 clients execute 1,000 queries, all these 1,000 processes will run concurrently, right? And they will try to take the CPU time. Of course, most of the work will be IO because it's a database. But sorting, think of sorting, think of hashing, think of join, think of like what merge sorts and whatever algorithms they use. This needs the CPU. And in this case, you will be just at the mercy of the operating system scheduler effectively. So that's not predictable. This is predictable when you actually have a specific sets of background workers and those do the work. And hey, they're busy, they're busy. That's it. You get the weight, you can measure the weight, you can know what's going on, right? So that background process, they are limited by something called the max worker process. A very interesting thing. Like that's the configuration you can set. Cool. So background workers, that's another pieces, that's processes. And again, those are spun up by the Postgres postmaster process. So they are fork. Everything is pretty much fork from this postmaster. All right, so let's switch to our auxiliary processes. Auxiliary means, that's a new word I learned because English is not my first language, so I'm learning a lot of stuff here. So auxiliary is like something that is a side process that helps things, right? It's a standby side processes. Helper, that's another word for it. And so the auxiliary processes, we're going to move them one by one, talk about them. The first one is called the background writer, not to be confused with the background worker. So the background writer, you see every time if you receive like an update statement from a user, it goes to the backend process. The backend process chooses to build a parallel plan or not a parallel plan, and based on that, if it's not a parallel plan, it executed itself, right? So there is like a nice work memory. I forgot to talk about it. This work mem live in both the backend process and also in the background workers, the parallel processes. And you do this stuff, and we change pages at the end of the day, right? What we do is write to this shared memory with our changes. So the dirty changes are written to these pages, and those pages become dirty, right? And when you write to the pages, when you write to also the wall, which is this append only mechanism for durability, right? We need to eventually flush it to disk for durability, right? They are only in memory. So this guy, background writer, its all job is wakes up and then flushes those pages to disk. Now, this is big difference. Background writers only writes to the OS. It says, hey, write. You know, the OS, actually, when you say write, it lies to you. It doesn't immediately write to disk. It writes to its own file system cache. And the reason it does that, because if I'm updating a file, like I say, I updated 1 byte in the file and I save, right? The OS doesn't really save to disk immediately. It stores it in its own cache, right? And then you change another byte, and imagine you don't have this cache. it will write it to disk, and you change another byte, it will write to disk. That will really issue so many IOs, right, to the disk, and it will slow down operations. It will slow down the bandwidth and the IO and the disk itself, and it will reduce the the lifetime of the SSD, right? If it's an SSD specifically, I'm not sure about hard drive, but SSD definitely, because you're gonna write to it, and these cells have lifetime. They have basically, each cell has, you can only write to it X amount of times. After that, it just burns, right? That's why SSDs have this weird leveling that just moves stuff along. It's, oh, you've been cold for a long time. Let me move you here and let me use your location to write more hot data. But yeah, so what the OS does is all writes, they cache things in memory in hopes that it might receive more writes, and we can flush all these writes at once. That's the hope. So the background writer just writes to the OS, right? Because it's fine. The background writer job is not really for durability. It's just for let's free up some stuff from the shared buffers, from the shared memory, because this shared memory is not unlimited, right? It's just whatever you configured Postgres to be. I think 128 megs is the default, which is very low, right? But as you pull pages in and you write to these pages, you want to read more pages, and sometimes there's no space in the shared memory, and you cannot operate on things that are not in memory, so you have to pull in memory. So the background writer will occasionally just wake up and says, okay, we don't have space, let me flush these dirty pages, flush them, right? And then empty them. Now I can put some more stuff. They go to the file cache, and then pooh. Eventually, the OS will flush them to disk. You might say, oh, what if we crash? We'll come to that. That's fine, right? This is the best situation where the database will not crash, which is 99.999% of the cases databases don't crash, right? It's the 0.1% when the database crash. We'll come to that, right? There's another process, which is actually the next one. It's called the checkpointer. The checkpointer's job is to actually says, you know what, all the wall changes that we did, all the pages we have, let's flush everything to disk, not to the OS. It will use a specific flag called the O_direct and says, hey, OS, I'm going straight to disk. I'm flushing everything to disk. Boom. So that when we flush all these changes to disk and we flush wall, it creates a checkpoint record that is here at this point and this date and this time and this second, we are consistent. Anything after that, we have to replay this data, right? But that's an important concept. The checkpointer creates a checkpoint after which we'll say, hey, we are actually good at this point. So it flushes everything to disk. So checkpointer is also another auxiliary process that is very critical, especially because the wall actually has a fixed size. It's not really unlimited. All right, the logger. You can enable logging by default to a standard output, standard error, to CSV in Postgres. And someone needs to wake up and write these logs, these errors to disk, right? To the logs. And that's the logger. Really nothing much to say of this process. So if you want to enable like tracing, you want to see what queries Postgres does, this is actually interesting. Auto vacuum launchers and auto vacuum workers. So what is vacuum, right? Vacuum, we talked about the architecture of Postgres being tuple based, like it's updates and deletes and inserts are all inserts, right? So you would get this bloat eventually where you have 100 tuples representing the same row, but all the transactions that needed those old tuples for multi-version concurrency control reasons are done, are committed. Those tuples have zero reasons to exist. Vacuum cleans those up, frees those up. Right? For us to actually use these pages to write more useful data. That's one job of the auto vacuum, right? But there's so much other thing. Vacuum does so much other stuff as well. And there is like so the auto vacuum launcher is the process that launches the auto vacuums. Just in case, for example, if it crashes, one of the auto vacuum workers crashes, the auto vacuum will start spinning those up until auto vacuum max workers parameter. All right, so the wall processes, I kind of combined all these guys into one. So we have the wall archiver. This is the responsible for backing up just the wall entry. The wall is very important because it has like a compressed version of the changes that the users made, right? Not the fat pages with everything, which is like the 8K pages, right? It's like very tiny, it will tell you the story of what happened. So the wall records are very, very critical, right? So that's what basically help us to recover in case of a crash. It will basically use this for replication. We push these wall changes to the replicas, and that's it. That we don't really need to change anything. There's just the wall entries is really just the DNA. If you think about it, it's the DNA of the database, right? Just everything is that we changed. So you can replay these changes in any database and you can get to the same state. So the wall archiver, the WA, archives entire wall changes for history purposes. So you can technically take the wall changes and replay from 0 to the state you have in the database. Right? Pretty cool if you ask me. Yeah? The wall receiver, so that's a process runs on the replicas that receives those wall, right? And you can write in any language you want, right? To as long as you understand the replication protocol. The wall, what is that? WW? What the heck is that? Oh, the wall writer, WW. The wall writer is responsible for writing the wall records and flush them to disk. You might say, isn't that the job of the checkpointer? Not really. Right? Remember, when we commit, we really need to make sure that the wall changes. That's the only thing we need to make sure. Committing a transaction, the wall must be on disk. I don't care about the pages, right? I don't care about the pages in memory. They can stay dirty, the changes that I made, right? But the changes in the wall must be flushed to disk. And once it's actually flushed to disk, returns access to the user, that's when you tell the user, commit success. If the wall is not flushed to disk, you can crash and you can lose everything, right? That's really bad. That's the job of the wall writer. Very critical job, right? When you commit, takes the wall writer, wakes up, says, like, let me flush that. Does that mean maybe the wall writer will actually flush even if your transaction didn't commit? You might say, what? That's absolutely fine. We have a record that says that this transaction is committed or not. So even in case of a crash, we're going to clean ourselves up. So don't worry about that. So flushing as often as possible. Checkpointer is actually flushing both the wall and the pages, right? And creates a checkpoint, right? That says, okay, this is where we are fully consistent. And this says that's the difference, right? We talked about that. The wall senders is basically in the client side, which is basically the master database, pushes the wall the wall changes to the replicas, right? Wall senders. And they have like max wall senders. You can configure that as well. And the final process, the starter process. And this is actually what I told you in the beginning. This is the first process that actually runs, even before the postmaster process. You see, let's say we have a transaction, we start a transaction, we start writing so much stuff, right? And we write to the pages, and we write also almost like 1 million records, right? The 1 million records will be really full-fledged rows in the shared buffer right here, and it will also be represented as walls, right? Wall changes, wall records in the wall, right? And when I say, let's say I committed, right, the transaction, right? So what we really need to just to make sure, let's say the checkpointer didn't run, right? Just the wall writer, and we committed, and the wall writer flushed all these changes, and then we crashed. So technically, pages are empty. We don't have, not really empty, but they have the original state where they were before my 100 million row transaction started. So the startup process, if once we started Postgres, the startup process restarts and says, okay, what was the last checkpoint? Well, the last checkpoint was this. Wow, that was like a while ago. What did we do since then? Right? We take that point. Since then, we inserted 1 million rows in the wall. Okay, there's the entries, good. But the pages are, oh, wow, they're really out of date. So what do we need to do? Spin it up, pull all these pages in memory, right? Before we start up the postmaster process and listen to anything, don't let anyone connect, right? Don't let anyone connect. Just spin up, apply all the changes in the wall to the dirty pages, make them dirty. And all of a sudden, now you got into the same state. This is called the redo, right? Literally go and redo all the wall changes, because technically you did them at once, right? At some point, you did them before the crash. Now you're redoing those wall changes to the dirty page, to the pages in the shared memory, right? Bringing them to the same state. Fantastic, if you think about it. That's why the wall is also called the redo log in other databases. Right? And there's also something called the undo log. Postgres doesn't really have undo logs. And the reason is because of this brilliant design of using tuples as the markup for the MVCC, right? Other databases use undo logs to record the old state, which is maybe if I do ever doing the MySQL NoDB architecture, I'll talk about that. But Postgres doesn't have to worry about the vacuum. Will clean those up, the old tuples, right? Even if you flush records that you technically didn't commit, a transaction that you didn't commit, that's fine. Transactions will know not to read those uncommitted tuples. So simple, because they will look up. So it's a little bit slower. They will look up and say, oh, I'm not supposed to read this this tuple, so I'm gonna ignore it. Right? And that lookup is expensive. So it's always like it's a two sword. What's it called? Two blade sword, double edged sword. Yes, 2-blade sword. What the heck? All right, guys. That's it for me today. I think hopefully you enjoyed this video. I thought I'll talk about this Postgres. It's so fascinating. I'm learning so much every time I go to this database. I'm learning so much, So I spend a lot of time in the doc and in the code to decode all this information. If you like this stuff, check out my database course, database.husseinnasser.com. Supports the show. Thank you so much.